자, 시작합시다. 오늘은 라이프 사이클 코스트에 대해서 말씀을 드리겠습니다. 지난 시간에 조금 말씀드렸는데 복습하는 의미로 반복해서 말씀을 드릴게요. 처음에 릴라이빌리티가 떨어진 값싼 그 제품을 구입하면 무슨 일이 생기는지 쭉 예측을 해봤고요. 꼭 그런 것은 아니고, 하여튼 릴라이빌리티나 퍼포먼스나 에피션시가 떨어져서 이제 처음 비용은 낮을 수 있지만은 전체 라이프 사이클로 보면은 그런 거 아니다. 그런 거 아닐 수 있다는 거 말씀을 드렸습니다. 그래서 라이프 사이클은 요람에서 무덤까지 프로젝트의 컨셉, 피저빌리티 스터디에서부터 가장 마지막에 디몰리션이나 디스포절 할 때까지 그 전체 과정을 말하는 게 되겠습니다. 그래서 라이프 사이클 코스는 그 전체 인간으로 치면 평생 동안 들어가는 돈이 되겠습니다. 비용이 되겠고요. 그래서 라이프 사이클 코스팅이다 그러면 그걸 다 이제 산출해내는 작업이 되겠습니다. 그래서 이제 라이프 사이클 코스트를 그 라이프 사이클 단계별로 여러 군데 적용할 수 있지만은, the most important stage is the stage of evaluating the alternative concepts. This is the most important area where we can apply the life cycle costing. This is the kind of annual accumulated expenditure on the project. As you know, the expenditure for the early stage concept design and feed is very low because only the human or engineering cost is relatively cheap compared to the equipment purchase or fabrication. So the cost is low. The growth rate is slow in the early stage of the project. And when we do some kind of fabrication and installation, the cost started to increase, and the real cost actually occurs during the operational cost. This graph is distorted a little in terms of time frame. So we think about the time frame, the conceptual design and the feed, it just are done usually 1 or 2 years. And basic and detail engineering, about three years. So we can say that we will take about 5 years from the conceptual design development to fabrication. The rest 20 to 25 years for operation. So the cost for operation is usually higher than the initial cost. So typically, we can say that 80 to 90% of LCC comes from the operation period. But the impact of the activity on the total cost decreases sharply. The impact of conceptual design on the total cost is very high. During the detail or basic engineering, the design change is limited. Simply, we cannot do much about the fixed design. The design change is limited to local design, and during the operation period, we are given a plant and we needed to operate the plant. So we cannot do anything, nearly anything about adjusting the life cycle cost, operation cost. So the impact of this activity decreased sharply. So that means that conceptual design is key to controlling LCC. But here we faced with some kind of dilemma. During the conceptual design, the information we have about the plant is very limited. We have only kind of sketch or some simple calculation. We don't know the details of the plant. So this is kind of dilemma. The conceptual design is important to control the LCC, life cycle cost, but the information available for us is limited. It is the case even for the risk analysis. Risk control in early stage is very important, but in order to estimate the risk, we need kind of detailed information of the plant. But we don't have. So we should be smart in early stage. So this is kind of cost structure. The life cycle cost can be divided into CAPEX and OPEX, capital expenditure and operating expenditure. CAPEX includes equipment purchase, the money required for buying the equipment, installation, and insurance. Do you have any insurance? You have medical insurance that may be covered by the school. Do you have any other insurance? No? I guess the guys from company already have some kind of insurance. Actually, I buy several insurance. So insurance is very important for the stabilized people. So anyway, the insurance talks when we have a big accident, right? So if the company, if the plant is subject to a big accident like a fire and explosion, the owner can reduce the damage, financial damage. OPEX includes energy consumption. In energy plants, this is the most important cost. Spare parts, roughly speaking, we need about 5 to 10% of the capital expenditure for maintenance. For example, what I mean is if our plant is $100 million, we need about $5 to $10 million every year to maintain, to keep the plant at the best status. So maintenance cost is very important. In the logistics support, we need personnel or some kind of support to deliver the spare parts, and the manpower, the operator's cost. So these are typical cost structure for land-based plant. So we need to pay attention to the unit of the CAPEX and the OPEX. CAPEX is one-time investment, so it is just dollar. But OPEX is annual expenditure. We need this kind of money every year. So the unit is dollar per year. So we needed to consider the equivalent value of the payment at different instant. Here is the concept of present value. Present value is the value of investment, payment, earnings, the money, are time independent. That $1 for the moment now, and $1 10 years later. So we can say that the former is more valuable. It's quite sure. So we needed to convert the money to the present value. What is the value of $1 10 years later? So we need to consider, first thing is interest. Interest, discounting, and the inflation. Let's consider one by one. Interest rate is the rate. You know very well about interest rate. We need interest rate to convert the value of your deposit in the bank after 1 year. So what is the worth of $1 after 1 year? So if you use the notation PV, present value, FV, future value after X years later, then we have this kind of relationship. Future value, 1 year later is equal to PV plus interest rate. So this is the equations. So if the interest rate is 10% per year, $1 right now is $1.1 after 1 year. This is the concept. This is the reason why we deposit our money in the bank. $1 after 2 years later, we have this kind of relationship. So it's kind of growth of our money in the bank with the rate of R, interest rate R. I think you already know this relationship. Discounting is that what are supposed to pay $1 after 10 years later. What is the worth of the payment? Can you understand this question? What we are supposed to pay $1 after 10 years later. For example, I promised Jungon that I will give you $1 10 years later. So I can lend $0.5, half dollar right now. Can I? So then Jungon should think about, do I have to lend $0.5, half dollar to the professor if I can get $1 after 10 years later? So we can you can reverse the relationship. So this rate is called the discount rate. So it's the decreasing rate of the money. One important thing is inflation rate. Inflation rate is that I can buy McDonald's hamburger paying $5 right now. Then how much do I pay to buy McDonald's hamburger after 3 years? Is it $5 or $6? So considering the cost of constituent of the hamburger, we know that the value of our money is decreasing with time. So this is inflation. The absolute value of our money is decreasing with time. So roughly speaking, so the future value is expressed by this way. This part, the numerator is the increase due to the interest rate. The denominator is the discount by the inflation. So usually these two rates are really equal. What I mean is that if the interest rate is 5%, the deflation rate is around 4 to 5%. What I mean is that the absolute value of our money, if what I mean that I can deposit $1 in the bank. After 1 year, my money will grow to $1.1, but the absolute value of the $1.1 is the nearly same that of the $1 for the moment, for the time being. Can you understand the mechanism? So if you deposit $1 in the bank, if the interest rate and the inflation rate are the same, are equal to each other, we cannot get any benefit by depositing our $1 in the bank account. Okay, the absolute value is nearly the same. But if we put the $1 in the drawer of our desk, the value and we cannot expect any benefit from the interest. So actually we lose 10% value after 1 year. I will show, I think I'll, this is the kind of application example. It's a cis carbon capture and storage chain design student project 2.5 years ago. This project was conducted by the student of our department. And the student project includes the design of onshore CO2 liquefaction and storage, a carrier, CO2 carrier, and offshore temporary storage and injection facility. It was a little big project. The student, I think it's 14 students has done this project about 3 months. They conducted the life cycle costing. So ultimate goal is how much is it to liquefy, transport, and inject 1 ton of CO2 along the CCS chain. So how much do we have to pay to treat 1 ton of CO2? This is the question they should answer. So what they should do is that they should estimate CAPEX and OPEX. That means they should design the facility and the carrier. So actually they did the design. Here DFO means the supply chain segment. D is the onshore facility to liquefy the CO2. F means Sorry, we'd better see this slide first. They divided the whole supply chain into three: liquefaction and storage, transport, and offshore injection facilities. So three teams designed the facility. Each supply chain segment, liquefaction process consists of compressors, some separators, and the transport included the CO2 carrier and the pressure vessels to store the liquefied CO2. And the offshore injection facility is kind of subsea storage and injection facility. So I'm a little confusing. What is F and W? CAPEX, OPEX. Anyway, they did. they estimated all the components. This is the unit cost element they estimated. For example, they estimate equipment purchase, installation, instrumentation and control, piping, electrical and building service facility, engineering supervision, contractor's fee, blah, blah. They estimated all the value. Can you believe this? Actually, we cannot estimate all the detailed component cost. So what we can do at the early stage is to estimate the main part of the plant or facility. Then the other costs can be estimated through a kind of proportional rate. For example, they estimate equipment purchase cost, but they do not rigorously estimate the cost of piping. But we know from the experience in this industry, the piping cost is usually, for example, 5% of the total equipment purchase. They kind of estimate had some uncertainty. The uncertainty is usually 30%. So we can say that their estimate has uncertainty about 30%. This is the cost they estimated. So the total cost of 20 years to treat 10 billion tons per year. This kind of CCS supply chain can apply to a big power plant. So they estimate all the cost, but the question is, how much do we have to pay to treat 1 ton? Treat means liquefy, transport, and inject. Okay, to treat 1 ton of CO2. So the answer was about $46. So we need $46 to liquefy, transport, and inject 1 ton of CO2. Over the whole CCS chain, the student did not consider the separation process. So if we assume that the separation process requires the LCs about $20 per ton, we can say that we need about $70 to separate, liquefy, transport, and inject 1 ton of CO2. We have here the explanation for the index. BC means onshore liquefaction storage, D ocean transport, E offshore temporary storage and injection. This is the whole pie of the LCC, the main part is OPEX D. OPEX D means ocean transport. So the ship consumes a lot of energy, and the CAPEX D has some substantial part. That means we need a lot of money to construct, build the CO2 carrier. And what is BC? CAPEX BC, the plant to liquefy the CO2. The CAPEX for the plant is relatively low in the whole pie of the LCC. But the OPEX BC, I think it's OPEX BC, not LC. OPEX BC is the operating cost for the liquefaction plant. So the liquefaction plant consumes a huge amount of energy. Let's return to the offshore plant. This is the intrinsic characteristics of offshore plant. Offshore plant is fixed and unique, safety critical, independent, varying operating condition, and we need kind of concurrent engineering, design, and fabrication. This is the characteristics I showed at the first class of this lecture. So this kind of cost structure is not enough for the offshore plant. So what I mean is we need to consider another aspect of the offshore plant. One is failure. Second is kind of accident-related cost. So failure means is the cost related with reliability. The maintenance in offshore is not as good as for the land-based plant. So maintenance is a really big job. So we should consider the cost for the reliability. So I name it failure risk. So one component is production loss. If a equipment get failed, the production rate can be decreased. So we need to consider the maintenance, the production loss. Second is the maintenance cost to fix the failure. Second is the accident to risk expenditure. I mean that if we have a big accident, we lose some production, and because of the accident, we may have asset damage. For example, our compressor can be damaged. So we need to fix the compressor by paying a huge amount of money. Another thing is fatality, the human life. So we need to consider this kind of cost. So this kind of cost has subject to uncertainty. So someone call it risk expenditure. This kind of cost is kind of fixed. If we have a plant, we can estimate the energy consumption, and the plant will consume the energy constantly. But this kind of risk expenditure is subject to uncertainty. What I mean is that we may or may not have accident. So it is related to the probabilistic nature of this cost. So we need to treat this component based on the probabilistic approach. This is an example of liquefaction process for LNG FPSO. You know LNG FPSO. LNG FPSO is to produce LNG directly from the gas offshore. So we have gas well here. The FPSO is floating. The FPSO throw in the gas and liquefy the LNG, and we have a shuttle LNG carrier. The LNG carrier will deliver the LNG liquefied inside to the consumer. This facility is called FLNG or LNG FPSO. But one big question is about the liquefaction process. Here is the background. One type of process, liquefaction process, is a mixed refrigerant process. This process is efficient. The energy consumption is very low, but the plant is complex and has a significant inventory. What is inventory? Hydrocarbon inside the process, inside the equipment. The inventory means hydrocarbon, the amount of hydrocarbon. That means the plant is efficient, but the plant is complex. That means it is subject to high failure rate and hard to maintain, and high inventory means it can have a higher fire and explosion risk. Another option is nitrogen process. Nitrogen process is less efficient. It consumes more energy than the former, but it is simple and no inventory. The nitrogen does not cause fire and explosion. So this process is efficient, but less unreliable, less safe. This process, nitrogen process, is less efficient, but more reliable and more safe. So which is better? So to answer this question, you should estimate the life cycle cost first. So we have this kind of term and we have risk X. So we need to consider this term. So another issue was the driver. The driver means steam turbine or gas turbine. Which option is better? The gas turbine is small. Steam turbine is also small, but steam turbine is big boilers. Okay, so the space requirement is bigger for the steam turbine. But gas turbine has higher failure rate and higher risk. It accompanies higher risk because it deals with the gas. Steam turbine only deal with steam. So we consider four combinations. NEST is nitrogen expander plus steam turbine, nitrogen expander, expansion cycle plus gas turbine, mixed refrigerant plus steam turbine, mixed refrigerant with gas turbine. So we compared four options. So first thing is we estimate the availability. How many hours do the alternatives operate in a year? So NEST, nitrogen expander plus steam turbine, has highest availability. So the operating time is is the first option, NEST, has the longest operation hour. This is a production loss that we can convert how much money we can lose because of the production stop. Because NEST has the highest reliability, it has the lowest production loss. This is kind of PLL is potential loss of life. It is the fatality parameter. So nitrogen cycle has around 70% of the mixed refrigerant cycle. So we can compare. So this bar represents the life cycle cost for life cycle cost without considering risk X, the reliability and failure. So in this case, the NEST is best. But if we consider risk X, life cycle cost is cost. So it is kind of minus for the installation owner. So the smaller the better, because life cycle cost is cost. So this mixed refrigerant plus gas turbine has the lowest life cycle cost. So the cost is the lowest for the last option. But if we consider the risk of equipment failure and accident, and if we consider additionally reliability and safety, NEGT are the lowest. What we can observe is that the life cycle cost is increased. The actual life cycle cost can be doubled for all the options, and the smallest is NEST and MLST. Okay, these are nearly the same. So the lowest is NEST. So what I wanted to talk about this is that the life cycle cost can be increased if we consider the equipment failure and accident, and the real the life cycle cost with risk X can be different from the LCC without risk X. In this case, that if we don't consider the risk X, MRGT seems to be the best. But if we consider risk X, these two options, NEST is the best option. So you should consider the risk of reliability and accident. But this is question about risk and the money. Okay, money is not everything in offshore plant. What I mean is, in offshore plant, the space is limited. Though another big demerit of nitrogen cycle is that it takes a larger footprint. Do you know the term footprint? Footprint is the space required for the facility. The nitrogen cycle has that disadvantage. It requires more space. So actually, the first FLNG ordered by Shell, manufactured by Samsung Heavy Industry, decided to adopt the mixed refrigerant refrigerant cycle. So I'm sure that they will recognize that the process is a little complicated. That means the production availability in real operation can be small than they expected. So currently the expert in this area started thinking that the process is too complicated. So we need to simplify the process. That means we are ready to accept some decrease in efficiency. Okay, we can that, but the net benefit can be positive. What I mean is that we can suffer some loss from the efficiency, but we can enjoy some increase in the reliability, production availability. So the net sum can be positive. Any questions? Life cycle costing is a little complicated, so I don't expect you to calculate the life cycle cost, but my emphasis is that you should consider the whole life cycle cost, and the cost for each stage. And another thing is you should keep in mind that the failure, the reliability, and the accident, in other words, the risk can have big impact on the life cycle. This study was published last year, and the CSS, the paper for the CSS was accepted by a journal. So I think you can see the details of the work the student has done. We talk about production availability without strictly defining the term, but my intention is that you should consider the production reliability, the failure or maintenance of the plant. So in this class, we will consider how to estimate the reliability of maintaining the system. So the reliability, the term reliability is used only for non-repairable item. So the term reliability of maintaining the system is availability. So reliability is used only for non-repairable item, non-repairable system. Instead of reliability, we usually use the term availability for the maintaining the system. So the correct topic would be availability of maintaining the system. This is the background. Failures happen, accidents happen. So if we have failure, we should shut down the component. So maintenance is applied to fix the failure. So operation is restarted. So the system is in operation and the shutdown stays alternatively. So the time, the operating period called uptime, UT. The shutdown period is called downtime. You know why we call them uptime and downtime? Because it is related with the production level. During the uptime, the production rate is up. So we call it uptime, and the opposite is downtime. In this figure, the plant is operating well for UT1. It had some failure of an item, so we need to shut down the plant. We call maintenance engineer, and maintenance engineers, they fixed the failure. So plant is restarted. Again, the plant is going well. After UT2, we have another failure to shut down the plant. So production availability. Availability is the fraction of uptime. So because the total period is uptime plus downtime, so the availability is UT1 plus DT1 plus UT2 DT2 over UT1 plus UT2. So this is the definition of availability. Actually, the real situation is more complicated than appears. The maintenance is consequence of failure, so it's a random process. But another thing we need to consider is maintenance timing. That the question is, do we have to do maintenance only after failure? Failure means sometimes a big accident. So we can approximate the question like this. Do we have to do maintenance only after accident? So some maintenance action should come before expected failure. Sometimes we can expect the failure. So there are two kinds of maintenance. One is preventive maintenance. Second is corrective maintenance. What is the usual maintenance we know is the corrective maintenance. We fix after we have failure. This is corrective maintenance. What is preventive maintenance? We apply some maintenance action before the failure. For example, I have 4 tires for my car, so I can replace my tire when I have a big car accident because of the tire. Another option is that I can replace the tires of my car after every 50,000 kilometers. So this the latter policy is preventive maintenance. So you can expect that the safety critical element should be maintained based on the preventive maintenance. Maintenance requires personnel, maintenance engineers, and spare parts. And but the maintenance engineer, the maintenance personnel should spend some time in inspection or checking. And there should be some kind of support to deliver the spare part. That kind of supply chain is called logistic support. So there are many things in maintenance. So we need a systematic approach. This is definition. It's not that important if you don't want to be a reliability engineer. So it's about notation, simple, very simple notation. xt1, xt is equal to 1 if the term is functioning at time t. xt is 0 otherwise, so it's a binary expression about the system state. Availability, the definition of availability is that availability is the probability that the item is functioning at time t. So it's the mathematical expression. The item is operating. xt equal to 1 means the item is operating. PR means the probability. So we can read like this. Availability is the probability that the state is not running. The item is running. Unavailability is just complement to the availability. So unavailability is 1 minus availability. It's the probability the item is not functioning. There are several definitions of availabilities. First is interval or mission availability. So our focus is the availability during the period from T1 to T2. So this is the definition of the availability, the mission or interval availability. If we start from, if T1 is 0, the equation is simplified to this. Another kind of availability, long run availability. I mean that here the tau goes to infinity. The limiting availability is the availability at a steady state. So if we consider the plant, the usual life cycle is around 20 to 30 years. Sometimes at the initial stage, we have some fluctuation about availability, but if you repeat failure and applying maintenance to the failure, we may have a steady state availability. That steady state availability is limiting availability. This kind of availability is important for the some systems which have a kind of fixed interval. For example, consider submarine. If submarine on the surface, it can take air and charge the battery, then it can dive. Usually it can stay under the sea around 2 weeks. So 2 weeks, the interval of 2 weeks is very important. The reliability and availability of the subsystems of the submarine for the 2 weeks are critical to the performance of the submarine. If it had some serious failure or accident, it should go to the surface. That means the submarine can be detected by ships or airplane. So in this case, the tau is very important. For the commercial plant, our interest is the limiting availability. How to estimate availability? First is reliability block diagram, fault tree analysis, Markov model, flow net, Petri net, Monte Carlo next event simulation. block diagram, we can estimate the reliability of a block diagram. Fault tree, Markov method, but as you know, as you already learned, Markov expression can be complicated if the number of components is increased. So to estimate the plant availability based on Markov process is limited. So reliability block diagram is fault tree, can be used, but usually we use reliability block diagram. And the embedded method is Monte Carlo next event simulation. So next week, after I'm coming back from Norway, we will learn how to apply Monte Carlo simulation to estimate the reliability block the production availability. This is the basic concept. Here is quality, reliability, availability, security, and safety. So let's digest the terms. What is quality? Quality is 품질 in Korean. What is quality? What is the quality of this bag? Second question is, what is the reliability of this bag? What is the availability of this bag? What is the security of this bag? What is the safety of this bag? So the definition is very important to answer those kind of questions. The first term, quality, is the totality of features and characteristics of product or service that bear on its ability to satisfy state or implied need. So the important term in this definition is implied needs. Some requirement for quality is clearly stated, but in many times the term quality has kind of an implication. What is the quality of this laser point? What is the quality of the bag? Design? Lifetime? So the quality had some drawbacks in engineering field because it had some implied need, not stated, not clearly stated implication. Second is reliability. Reliability is the ability of an item to perform a required function under given environmental and operating conditions and for a stated period of time. So reliability, in order to define reliability, we need to define three. One is function. Second is operating conditions, operating environment. Third one is the time interval. So reliability is the probability. Third one is availability. Availability is the reliability of the maintained system. Under the combined aspect is reliability, maintainability, and the maintenance support. So reliability is the availability is the reliability plus maintenance. Security, we can define security. Security is the dependability with respect to prevention of deliberate hostile actions. So security is the action against theft, just theft. Safety, freedom from those conditions that can cause death, injury, occupational illness, or damage to a loss of equipment or property. So acceptable level of risk is related with the safety. So safety is also hard to define. So we instead defining safety, we usually define risk. Okay, risk is easy to define. What is risk? frequency times consequence. Never hesitate. If you are asked what is risk, just answer frequency times consequence. So the reliability engineering or availability engineering can be applied to various industry, but the quality engineering or quality control is usually based on reliability engineering. Safety engineering. I'm not quite sure we use the term safety engineering. And when you annual risk analysis, we use the term risk analysis or risk management. Reliability, maintenance, availability is function of inherent reliability, maintenance, maintainability, and maintenance support. These are three components of availability. What is inherent reliability? Inherent reliability is component reliability and the system configuration. So it's the basic. It is related with the failure rate of the system. Maintainability is the easiness of access, dismantling, and reinstallation. So it's the action directly related with the maintenance. But as you know, the maintenance needs more logistic support. So maintenance support means maintenance personnel, skills and tools, and availability of support. So maintenance is a very complicated activity. This is the definition of maintenance. IEC. IEC is International Electrotechnical Commission. And the combination of all technical and the corresponding administrative actions, including supervision actions intended to retain an entity or restore it to a state in which it can perform its required function. In a traditional sense, to correct the failures by learning about the system is the maintenance, part of maintenance. Better knowledge on the system, better maintenance. We usually assume that. And scale of maintenance personnel was critical. This is a traditional belief on the maintenance. So in short, in a traditional sense, we need an expert. He's a kind of God. For example, he can, by listening to the engine noise, he or she can know what's wrong with the car. Actually, there are those kind of persons. There are those kind of godlike maintenance engineers in many, many areas. This is the traditional belief in maintenance. The question is that the traditional concept is reactive to the failures. It is possible to do proactive maintenance before failure. What I mean is that the expert know the failed item if we have a failed item. But can he or can she know if the failed item before the failure? This is the first question. Second is it possible to design the system for better maintenance? The maintenance engineer is maintenance engineer, not a design engineer. So is there any smart way to design the system to make the maintenance easier? third question is, how about the system design, incorporating maintenance, planning, and the safety strategy? I mean that maintenance, for example, the maintenance engineer, depending on the system design, the maintenance engineer can replace the item, or the maintenance engineer can fix the item. If we have some problem, assume that this is the part of my engine. If I have some problem, the maintenance engineer can fix this item, or he can replace the item. But this kind of strategy can be considered from at the very beginning stage. At the design stage. The designer can design the system that if this item had some kind of failure, this item should be replaced with a new one. So the designer designed that part that replacement easier. So if you have a car, you are very familiar with this kind of things. These days, 10 years ago, if we have some problem with our car, the maintenance engineer tried to fix the part, the item. These days, they just replace the whole component. So this kind of strategy, as you may expect, is quite related to the company strategy. Considering the fact that OPEX, operating expenditure, is considerable compared to the CAPEX, the money we need to maintain our car compared to the money we should spend in buying our car. The choice the car company can make is that they design the car to take the strategy, replacement of the part. So this kind of strategy can be incorporated from the very beginning stage, design stage. So last is any mathematical models to answer the question. This kind of things depends on kind of a hinge or sense. But is there any way to mathematically model these kind of things? So there are three types of maintenance. I already explained the two maintenance. And another is failure finding maintenance. I will explain this shortly. Corrective maintenance, called the CM usually, is action after failure. To bring the failed item to a functioning state by repairing or replacing with the spared one. There are two kind of approach: to fix the item or to replace the item itself. So this activity is called repair. Corrective maintenance is called repair, or breakdown maintenance, or run to failure maintenance. Can you understand this term? Run to failure. So we leave the item run to failure. We just wait until the item runs to failure, until failure. So this maintenance policy is called run to failure maintenance. Run to failure maintenance is just corrective maintenance. Preventive maintenance is kind of action before the failure. So we need some kind of strategy or policy to apply this maintenance strategies. One is age-based, second clock-based, third condition-based, third opportunity maintenance. What is age-based? we check the age. If we consider the tire of my car is a very popular object in my class. For tires, I replace my tire every 3 years. This is the age-based maintenance. Clock-based is I replace my tire every 50,000 kilometers. So it's related with the clock and the operating time. The clock here means the operating time. Age is the calendar time. Okay? Condition based, I check the condition. Then, if I find some kind of clue to failure, I replace my tire. Usually, I check the surface of my tire. I check the roughness of the tire. So if it is a little wear out, I change my tire. That kind of policy is condition-based maintenance. What is opportunity? I'm very lazy, so I don't want to go to the mechanic frequently. So I have some problem with one of my tire, so I replace the other 3 when I visit the mechanic. This kind of maintenance is called opportunity maintenance. My laziness is kind of extreme case, but consider the real situation in plant. If we apply some maintenance action, we should stop the plant. We should dismantle some part, and we apply some maintenance action. So if we have second failure, we should repeat all those kind of actions again. So it's very good opportunity to reduce the risk of second failure. So it's a very natural way of maintenance. Failure finding maintenance is the maintenance to find the failure. This kind of maintenance is usually for the safety systems. That we test the plant or the system or safety system to find the hidden error, hidden failure. Hidden failure is hidden during the normal operation, but we can find the hidden failure by directly testing the item. For example, we have gas detectors here. We don't know normally if the detectors are functioning correctly or not. So the gas detector may subject to hidden failure, but we can apply some real gas. We can test. We apply small amount of real gas to the detectors. This kind of maintenance is called failure finding maintenance. Gas detectors is a small example. It may look not that important maintenance, but consider the safety system in an offshore plant. There are hundreds safety systems, so usually there is a regular check or regular shutdown of the whole plant to find the hidden failures. So it is a really big job for offshore installations. There is a trade-off. You may expect corrective maintenance. One disadvantage is that the production loss or to failure or the accident we should accept. Consider the tire of my car. I can have a big accident because of the failure of my tire. Preventive maintenance is good, but a still good item can be replaced. I replace my tires every 50,000 kilometers, but they can be still good. So it's a kind of wasting of money and resources. So there should be kind of optimization. So please read section 9.6. So each policy has its own pros and cons. So there should be an optimum by properly mixing them. These days, the kind of maintenance is a big business in every corner of our life. But in industrial area, even in it is the case even in the industrial area. For example, think about the ship machine. It's think about the ship machine, ship propulsion system. Ship propulsion system is about $10 million. But the money is small compared to the cargo the ship carries. So the stop of the ship engine can cause many damages. So the kind of condition-based monitoring, the measuring the temperature, pressure, vibration of the engine and the maintenance based on the information. This kind of maintenance is called the condition-based maintenance, as already we learned. That kind of technology is currently in application.